So we have this formula. So let's stick with WASP-19. We know the luminosity of the star, slightly less than the sun. This is for the planet, see the B. This is the distance. It was very close, so we're expecting something. So we'll put those numbers in here, and then we find this. So there's an assumed albedo of 0.16. If you want to know why, read this article. Good luck. But it's I mean it's scientifically grounded that they have this number. Okay, so it's not just a guess. It's an educated guess. And as you can see, we find this temperature in Kelvin. If you don't know what it is, it's more than 1800 degrees centigrade Celsius. So that's really hot. But of course, it's much closer to its star. So yeah, that makes sense. Okay. So far we know this. From transit observations, we can find the radius, the size of the planet, and then with the period, we can find the orbital radius, so the distance to its star, and then we can calculate the equilibrium temperature, which is a sort of measure of the temperature of a planet, right? For most planets in our solar system, it pretty much works. So this is pretty good, but we want to know the mass of the planet. We don't only want to know the size. We want to know what type of planet it is. Is it the gas giant? Is it the ice giant? Is it the rocky planet? So we need to know the mass, and then we can find the density. And well, that's stuff we can do. So for the mass, we need this. So you know, if you swing a huge weight, then basically it depends on the length of wire and the weight, how much force you should apply. So we know that for a big weight, a large mass, we need a short arm, and then on the other end we have a small mass with a large arm. So this moves with a big radius, this moves with a small radius, and we find this. You've seen this law before, I guess. So we can find the mass of the planet by making this approximation, and don't worry, because basically this drawing is not correct. In reality, even with Jupiter, and Jupiter is really a big, massive planet, it's only 1 promille, 1,000th of the whole distance. So this distance here is 1,000th of this whole distance. So this is a pretty good approximation. Don't worry about that. So even for really heavy planets. For lighter planets, it's even better. So we don't worry about that. So this is an approximation. So and how it looks is like this in animation, of course. So a top view and a side view. You see that the star also moves because of the planet. They spin around a center of gravity. It's not that the star is standing still and the planets rotate around that. No, they both rotate around their center of gravity. And the heavier the planet is, the bigger the orbit of the star. So if you look from a distance, you don't see the planets themselves because they're really weak, but you see the star, but you see the star moving, right? If you're looking from the side, you see the star moving a lot, towards you, away from you, towards you, away from you. If you're looking at it from the top, basically you don't see it moving towards you. You see it wobbling like this, but not towards you, not like that. So the thing is, sometimes we don't know what the angle is, so that makes it more difficult. But let's take this formula and see what we can do, right? So we had Newton who said, well, there's a law of gravitation and the centripetal force, and now we have this formula, and we can combine that with magic and then find this formula, right? So this formula is very nice because it has the mass of the planet, some constants here, the period, which we know from the observations, the mass of the star, which we know from the light of the star basically, and now we need the velocity of the star too, right? So basically with those variables we can find out what the mass of the planet is, right? So, okay, sorry. It works. So what we know is that for that formula we need the gravitational constant, the period in seconds, the standard unit, the mass of the star, and then we need the velocity of the star. And for the velocity of the star, we do the next thing. We well, look at the star, so we have this top view or the side view or something in between, and we know that if we see a star move, if it's moving in, if we are looking in the side view, then the velocity you see now is the actual velocity of the star, and then backwards. But if it's on the side, then basically you see only a part of that. So it's partly moving front and back, partly moving up and down. And this front-back velocity is what you measure. So it might be less than the actual velocity. So what we do is basically look at the actual velocity of the star, and this is what we measure. So that it has to do with the angle. So if the angle is 0, so this case, then we don't see any movement of the star, not towards us or away from us. If it's 90 degrees, it's this, then basically what you see is what it is. And if it's in between, then yeah, well, it's in between. So basically the velocity we measure is always going to be smaller than or equal to the actual velocity of the star, which means, I have to take that into account, which means that in this formula, this V might be, in actuality, might be more. So the mass we find might be more than what we calculate, right? So, if a light source moves, if it moves towards you, the light waves are compressed. The wavelength gets shorter, light gets bluer. If a light source moves away from you, light waves get stretched. So the wavelength is longer, redder light. We know this from sound, from I don't know, car horns that pass. You know that the tone goes up or down or whatever. So that has to do with the compressing and stretching of the sound waves. Same works for light waves. And it works like this, that the change in wavelength divided by the wavelength of something itself is the velocity towards you divided by the velocity of light, c. And if you look at the light of a star, you see absorption lines from elements. So we can see the lines in the star, and if those lines move, then we know the star is moving towards you, away from you. The lines go to the blue, it's moving towards you. If it's moving to the red, it's moving away from you. And if you see this regularly, and you can measure this, well, this is really big, but if you can measure this wavelength variability, then we can calculate what the actual velocity of the star is, right? So that's the Doppler effect. And we can do the very precise, as you can see, these are really tiny numbers. So visual light is roughly 500 nanometers, and this is really a tiny amount. So we can really measure this velocity very precisely. Okay, yeah?
Question,
yeah.
So the light, the energy pushing in the opposite direction for it to forecast, is that maybe then a negative gamma?
Gamma? What gamma do you mean?
Like the gamma radiation.
Gamma radiation?
Yeah, the gamma radiation, negative gamma radiation.
No, I wouldn't. No, if a light source moves away from you, basically the wavelengths are stretched, so the light that you will see will have less energy, and if it's basically moving towards you, it's compressed, and you have a higher energy. So what you measure has higher and lower energy, higher, lower, right? Because basically the energy is compressed, but you won't get negative energy, but more or less, so that the energy level of the light changes. Yeah, that's what you see.
Okay.
So, time for another reality check, don't you think? So let's see. Astronomy is basically about this. I told you about Betelgeuse. Betelgeuse is a really big star, relatively close, but most stars are much smaller, much farther away. So it's no use zooming in. If you see pictures with a nice round dot, basically that's the light splashed over all kinds of pixels. But basically a star is really, really tiny. If you take Betelgeuse, I have to check the numbers here. Betelgeuse, if it is as big as a euro coin, I'd have to place it 76 kilometers away. And other stars are smaller than that. So imagine, if you can, looking at a euro coin at 76 kilometers. That's ridiculously tiny. You need a really good camera to see this disk. And that's what we can do with Betelgeuse. But most stars are farther away and smaller, so forget about it, it will stay a dot. And from this dot of light, we can do all this stuff. So what we can do is we can measure the amount of light. That's basically what we do with the transit method. We measure the light intensity, and then we see this dip, and we see it again, and then we can find out stuff. Or we can radiate the light through a grating or a prism and spread out all the colors and measure all those colors. And then we find the light distribution over the wavelengths, and then we can find temperature, and we see the lines move and stuff like that. To capture that light, we need a CCD. A CCD is basically an electrical device that collects photons, and then after it stacks a number of photons, it has a charge, and then you can read the charge. So it turns light into electricity. You all have CCDs in your mobile phones, in the cameras. they contain CCDs. Before that, we had photographical paper that was a chemical layer on paper that was sensitive to light, but now all we have is CCDs, and that comes from astronomy. Because astronomers are not people that are really behind telescopes with their eyes, sometimes, but we want to do measurements, and we want to collect light for long duration, so we need this equipment. So we used photographic plates and photographic paper before, and now we use CCDs to collect all that data, right? And basically from that, well, they commercialized it, and now everybody has CCDs in their cameras. So that's a nice thing, I think. So back to the formula again. So now we want to find the mass of the planet. We know the period, we know the mass of the star, we know the velocity now from the Doppler method. So let's fill in these numbers for tau Botis. So that's just a star in the constellation Botis. And this is huge, by the way. So we find this mass. 5 times, more than 5 times Jupiter. So this is really a really massive planet, right? Really big. So you get images like this. So this is that star, and relatively close, as you can see, we find this planet, which is sort of Jupiter-like. Okay, so this is an illustration, and well, might look something like this. Okay, but usually stars are much further away. But this planet is close to the star. So that's how we get those pictures, because of the numbers, and they are based on actual science and observations. Right? It's not just made up.